Hi, in this video, we'll be continuing our study of statistics, and in the last video, we have introduced what is a sample mean and sample variance. So, in this video, we shall look into the usefulness of a sample mean and sample variance. In particularly, it is used normally to estimate the population parameters. That means the whole population you gather, you find its mean and you find the variance. These are the population parameters. So then we are particularly interested in the sample mean in this situation. So everyone got like some value and then you just take the average. But there's also another case of a population whether you just have let's say a population of humans and then just ask whether you are male or female. So you have then this case is known as the dichotomous case, but basically it just means that the random variable is a binary one, so it takes on the value 0 or 1. In this situation, the population mean is known as the proportion. So the population total is just taking the mean multiplied by the total number of people, which is n. And the population variance is given by this formula. And what's useful is when you expand out the equation, you get this. But this is already known, as it just looks like the normal variance formula that we already have. But now in the dichotomous case, you can imagine a dichotomous case to be like a balloony random variable, and so the variance will be of the form p bracket 1 minus p. And the population standard deviation is just the square root of the population variance. So a random sample must also be representative, because if it's not representative, then it cannot be a good estimator for the entire population. In particular, as n gets larger, the sample mean will be closer to mu. And we say that these x1 to xn's are representative of the population, are likely representative of the population. Likely because we might be unlucky in a sense that all the realizations are the same. So representative means you have it really represent the population distribution. We might say x1 is representative of the population, but this is odd because it only gets a better estimation of the population once n becomes larger. So why do we care so much about sample mean? Is because if we consider this sample mean, it has its own distribution known as the sampling distribution. And what we really like is to use this sampling distribution to determine how accurately this x bar will estimate mu. So let's speak of some lemmas first to get us off started, or what this actually means. And so let's just say you have a PMF for a discrete random variable of the following form. Then the expectation of xi will be mu and the variance of xi will be sigma squared. How do you prove this? Well, it's just a simple calculation from the definition of xi. So xi just equals to the sum of little I probability of xi. I goes from 1 to m. What's the probability? Well, it's just nj over n. So you take out the 1 over n since it's constant. So what's nj? Epsilon j. Well, epsilon j is the distinct value and nj is each value. then this sum will just be mu. And for variance, you can again show that it is just sigma squared, and this proves the lemma. So with this lemma, it just tells us that, okay, yeah, I got a representative from the population, and I calculate its expectation. It is supposed to be the mu, of course, because it came from the population, so it is quite intuitive. And with that, now you can actually find that the expectation of x bar equals to mu, because expectation of x bar equals to the expectation of 1 over n times the sum of xi's. Then this is just 1 over n times the sum of xi's expectation inside. But what's the expectation of xi? Xi is mu, and then you got n of it, so these n's will cancel out, so you're just left with mu. And the corollary, of course, is the total is just going to be mu times the total number also. In this case, because the expectation of x bar equals to mu, we can say that x bar is an unbiased estimate of the population mean. So what does unbiased estimate mean? It means that when your expectation of some estimator, let's just say x, it equals to the population parameter that you want. And actually, the mean square error equals to the variance plus the bias squared that we have already understood from an earlier video. When x bar is unbiased, it means that this mean square error is just the variance, so there's no bias. And if we were to actually calculate the variance of x bar, you can just see, and you realize that the variance of x bar is sigma squared over n. And then you just take the standard deviation of it, and this standard deviation of the sampling distribution will be known as the standard error. So it is the error or the spread of your x bar, not your x. So standard error is for your x bar, and this is the standard deviation, which is sigma over square root n. So because the SE is this, we need to estimate now. The need to estimate sigma might give the impression that the ST fluctuates as well. So an intuitive estimation of this sigma squared is the formula that is very natural over here, because this is like variance, so you want to take the xi minus x bar whole thing squared. But what's happening is your x bar is estimated from all these xi's, so this is not the true population already. That's why this is just an estimation. So instead, we need to take into account of that, and instead of dividing by 1 over n, you divide by 1 over n minus 1. And the reason for that is because when you divide by n minus 1 and you take this expectation now, this actually becomes equals to sigma. And because this equals to sigma, we say that this sample variance formula is now an unbiased estimate of the variance. So you can actually just verify that yourself. So in conclusion, our mu will be just around x bar, give or take s over square root n. Meaning you got a mu here, and then your x bar can be like distributed along here with a standard deviation of s over square root n. Okay, so earlier whatever we did was sampling without any with replacement, because the probability remains the same for everyone. But now if we take into account that you have sampling without replacement, meaning the probability actually can change, then this induces a dependence among the xi, and we'll see why. However, if our population size is very big, then this dependence becomes very small, and our result will still be a good approximation. So the first thing we need to do is we need to recognize that without replacement, now the covariance is no longer 0, and this will be the covariance given minus sigma squared over capital N minus 1. Using this, we are able to get that so how do we prove this is we just use the identity for the covariance over here, and with lots of algebra you actually see that it's not really much of a conceptual thing, because it's really just writing out the what does this mean. You just write out everything in full, and then you just try to calculate the conditional probability, which of course is the number of people over n minus 1, and then n minus 1 over n capital N minus 1. Then when you sub everything back, then you actually get to simplify it. So it's really more of an algebra thing, and I'll leave it to you to read this lemma proof by yourself. But what you need to take note is that the covariance is of this formula. And with that formula, we are now able to calculate the variance of x bar, and it is actually going to be this. Reason, okay, so variance of x bar is 1 over n squared, then the sum of all these covariance. Then all these covariance, when the I and j are equal, then it becomes variance. So you have two sides. You got 1 over n squared times this sum of variance plus 1 over n squared times this sum of covariance. The variance sum, you just need to add them all together, so it'll be like n times sigma squared. So it's just sigma squared over n. Then you minus, then this covariance, we already have the formula, so it's over here, which gives us our desired result. So what we see is that the variance over here of the sample mean without replacement now differs by the actual sampling variance, which is this, by a factor of this. And this is known as the population correction. And in this case, you actually see that if this n is very large compared to this sample size, your population very big, then this part will be very small, and then it will just be 1. And then you say that x bar will actually be just reduced back still to an estimation approximately this, which is what it is with when you have replacement anyways. So that's all for this video, where I introduced to you what is a population parameter, and in the case where there's two. So in one case you have your mean, your sample mean, and in another case you have your population proportion. So then I bring you into seeing why the sample mean is actually an unbiased estimate of the meal, and why the variance is not. So instead you need to use the sample variance. And I give you another example where now sampling is without replacement, and we see that it actually has a dependence between the xi's. But this dependence is weak when the population size is very big. So that's all for this video. I hope you have enjoyed it. You can look through this again, and I'll catch you in the next one. See you.